We're going to take our next step on our investigation into polynomial functions. So this is part 3, and it corresponds to section 7.3 of the textbook. We're going to get into some new vocabulary, and I'm going to try to motivate our next step with an example. And if the example gets a little bit confusing, just hang on till we get to the exercises. And I think when we do our summary and the exercises, that may clear things up. But I want to try to go through this little discussion first. So some vocabulary. Zeros of a polynomial. Let f of x be a polynomial function. The values of x for which f of x equals 0 are called the zeros of a polynomial. This is really just like x-intercepts. I guess technically I should say the zeros are the x-coordinates of the x-intercepts of the function. And we've already looked at some examples of x-intercepts on our of polynomials, right? So example 1, we've looked at the function f of x equals x cubed minus 3x, and we graphed it. There's a little version of the graph here on the side. So we would say the zeros of this polynomial are 0, square root of 3, and negative square root of 3. Another example that we just graphed recently was this f of x equals negative x to the 4th minus x cubed plus 6x squared. And we found its x-intercepts as we drew the graph. So for this function, we would say 0, negative 3, and 2 are the zeros of the polynomial. They're the x values that when you plug them into the function, you get a y value is 0. Another example we looked at was x minus 2 cubed. We saw that that function has only one x-intercept, so it has only one 0, x equals 2. But because that factor occurs to the 3rd power, we say that 2 is a 0 of multiplicity 3. The multiplicity matches the exponent on that factor. Now, here's an example we haven't looked at yet that we're going to start looking at a bit. F of x equals x plus 2 cubed times x minus 4 squared. So I think you can see that this polynomial has two zeros, negative 2 and 4. They'd be the x-intercept values for that polynomial. And we say that negative 2 has a 0 of multiplicity 3 because of the exponent there. And 4 is a 0 of multiplicity 2 because of the exponent that occurs in this expression here. The multiplicity of a 0 tells us something about the shape of the graph near the corresponding x-intercept. So I want to investigate this a little bit before I give you a general rule. So we're going to look at this same example of f of x equals x plus 2 cubed times x minus 4 squared. It has two zeros, like we just said. First, let's look at the 0 x equals 4, a 0 of multiplicity 2. And what I'm going to do is I'm going to look at values of x very, very close to that 0 of 4. So I'm looking at a value of x slightly smaller, a value of x slightly larger, and I'm going to plug into the function expression. And I'm not going to figure out the whole value here. I'm just interested in whether we're going to get a positive or a negative y value. So let's see when we plug in 3.9 plus, that's plus 2 cubed, that's a plus sign there, times 3.9 minus 4 squared, I get 3.9 plus 2 is 5.9 cubed 3.9 minus 4 is negative 0.1 squared. I'm not going to figure all this out. I just want to know, am I getting a positive or a negative y value? 5.9 cubed is positive. I have a negative 0.1, but when I square it, I get a positive. So this is definitely going to come out to be positive, a positive value. Now at 4, of course, if I plug in 4, I'm going to have 4 plus 2 cubed times 4 minus 4 squared, which is 6 cubed times 0 squared, which is 0. And of course, that's what it means for 4 to be a 0. When we plug it into the function, we get 0. At 4.1, when I plug in, I'm going to get 4.1 plus 2 cubed times 4.1 minus 4 squared, which is 6.1 cubed times 0.1 squared. Positive times positive is positive. So what we care about here is that when we look at the graph, so this is a portion of the x-axis. I know I have a 0 at 4, but what we're seeing is that slightly smaller than 4 at 3.9, we're getting some positive. I'm just going to write a point on the graph above the x-axis, some positive y value. And slightly larger than 4, we get a positive y value. So this is meant my attempt to convince us that the graph is going to do this kind of shape at that 0. It's going to come down and touch the x-axis at 4 and then kind of bounce back off. It's not going to actually cross the x-axis. And that has something to do with this multiplicity of 2 for that 0. Let's look at the other 0 for this function, the x equals negative 2. It's a 0 of multiplicity 3. And I'm going to do the same kind of analysis now with values of x very close to negative 2. So I'm going to plug in a number slightly smaller, slightly larger than negative 2. So I get negative 2.1 plus 2 cubed times negative 2.1 minus 4 squared. This is going to be negative 2.1 plus 2 is negative 0.1 cubed times negative 6.1 squared. Now a negative number cubed is negative. A negative number squared is positive. I'm multiplying a negative times a positive. So I'm going to get a negative result, negative y value at negative 2.1. At negative 2, I shouldn't even have to write this down because I'm going to get 0 cubed times negative 6 squared. Of course, 0 times anything is 0, and that's why we call negative 2 a 0. The y value there is 0. And now I'll plug in negative 1.9. Into the function. Negative 1.9 plus 2 is a positive 0.1 cubed. And then I get negative 5.9 squared. So here I get a positive times a positive, which is positive. So on one side I'm getting a negative y value. On the other side of the 0 I'm getting a positive. At negative 2.1, the graph's got to be below the x-axis. At negative 2, it's right on the x-axis, that's the 0. And at negative 1.9, we're positive. So this graph is crossing over. And it's got something to do with the 0 of multiplicity 3. Now here's sort of the gist of it, which goes like this. If you have a 0 of multiplicity 2, so that factor looks like it's squared in the original polynomial, you're going to get the shape of the graph is going to look a little bit like x squared, y equals x squared, close to that 0. If you have a 0 of multiplicity 3, close to the 0, the graph is going to look kind of like y equals x cubed as we pass through that x-intercept value. And what I want to do here then is just, let's put together a sketch of this function before we move on to other examples. So I want to sketch a graph of x plus 2 cubed, x minus 4 squared. And before we do it, I want to analyze the end behavior also of this function, because this is something we're going to always have to do. In order to get the end behavior, I need a degree and I need a lead coefficient. Now, we're used to seeing the degree when the polynomial is multiplied out. And I don't want to actually multiply this polynomial out. I want to just be able to think about what it would come out to be if it were multiplied out. Now that x plus 2 cubed stands for x plus 2 times x plus 2 times x plus 2. X minus 4 squared is x minus 4 times x minus 4. If I were to multiply this out, can you see that the leading term is going to come from these x's being multiplied together? X times x times x times x times x. I'm going to end up with an x to the 5th leading term plus other terms. And you can just go ahead and start multiplying it out if you want to check on your own, even though it's a bit tedious after a while. And so the degree of this polynomial is 5. And the lead coefficient, since that's just x to the 5th, it's 1x to the 5th lead coefficient is 1. And this tells me about the end behavior, right? So the end behavior is like y equals x to the 5th, which has a graph kind of like so. Okay, now let's go ahead and I'm just going to do a rough sketch of this function. I'm not going to plug in any x values. I'm just going to use what we figured out so far about this function now. 1, 2, 3. We know we got a 0 at 4 and at negative 2. Again, notice I'm using that language as 0. That's just like saying x-intercept. The end behavior is like y equals x to the 5th. So beyond 4, we know that graph should be taking off in a positive direction. When we're less than negative 2, we should just be falling off to negative infinity. Now, on the page before, we did a little bit of analysis of the using the multiplicity of the zeros. Because 4 has multiplicity 2, we know the graph looks like kind of like a x squared graph close to that point. It doesn't cross through the x-axis to the other side. At negative 2, which is a 0 of multiplicity 3, the graph looks kind of like, close to that point, a copy of x cubed. So now I know my end behavior. I know I have to cross through the negative 2, 0 in this way. Somehow I have to get over to the 4, 0. Well, somewhere I just turn around here. But then I just bounce off the x-axis and take off again, okay? So there's a rough sketch, a pretty good sketch of what this polynomial function looks like. X plus 2 cubed times x minus 4 squared. All we used was the end behavior and the information we learned about the graph around the zeros based on the multiplicity. And I think I just want to make this statement before we finish this segment of the video, because this sums up now, if anything seemed unclear about this discussion about multiplicity, this is what you got to know. The multiplicity of zeros in graphing at a zero, like an x-intercept, of even multiplicity, the shape of the graph is going to be either shaped like so, like y equals x squared, or the opposite of that. Could be like minus x squared, if like the function might be negative on both sides of that. But it doesn't cross the x-axis. It just bounces off above or bounces off below. At a zero of odd multiplicity greater than 1, the shape of the graph is going to be either like this or like that. Again, depending on where other points are located. There's going to be a little bit of flattening because it's going to appear a little bit like either x cubed or x to the 5th or x to the 7th, whatever its multiplicity is. If the multiplicity is 1, if you have a factor just occurring to the first power, then the shape of the graph is, we didn't look at an example of this, but this is what's going to happen. We're just going to kind of cross over. We're not going to flatten out. We're not going to turn around. It could be curvy, could be kind of straight, but we'll be able to tell from the particular graph we're working with. Multiplicity 1, we just sort of shoot right across the x-axis. So I'm going to stop this, and we're going to do some examples in the next segment. We'll do some exercises.